Hello everyone, my name is Anushri, second year BE in Information Science and Engineering student at Sri Venkateshwara College of Engineering, Bengaluru. Today's topic of my presentation is InterProcess Communication. Contents. Process. InterProcess Communication in Linux. Types of InterProcess Communication. Signals InterProcess Communication System. Dbus InterProcess Communication. Uses of Dbus. Features of Dbus. Why Dbus and conclusion. What is a process? In an operating system, a process is a fundamental unit of execution. When a high-level programming language is compiled, an executable file is created, which can be considered as a process. This process can be invoked by the scheduler, which determines when and how to execute the process without requiring the human intervention. This operating system plays a crucial role in the management and operation of a system since it runs various processes as needed. It handles tasks ranging from the process creation to process termination. In Linux systems, processes are usually created by duplicating an existing process known as the parent process through a mechanism called as forking. When a process needs to be created, a new process, it executes the fork system call. The process that starts the fork is known as the parent process, and newly created process is known as the child process. After forking, both the parent and the child processes continue their execution from the moment of the fork, but they have independent execution spaces and states. What is interprocess communication in Linux? IPC in Linux refers to the mechanisms and techniques that allows processes to exchange information, share resources, and communicate with one another. This involves synchronizing their actions and managing shared data. IPC in Linux allows processes that are running on the same system to communicate, coordinate, and exchange the data. Considering the following scenario, you have a client and server application. The client and the server are independent processes that operate on the same Linux system. The client makes requests to the server, which processes the request and returns responses to the client. This communication can be established via inter-process communication mechanisms. IPC involves indirect communications, pipes, message queues, FIFO, shared memory, message passing, direct communication. Types of interprocess communication. The Linux kernel has many IPC mechanisms that allow processes to communicate and collaborate. Processes can exchange information and synchronize their actions by using the IPC mechanisms provided by the Linux kernel, enabling the efficient and cooperative system operation. Here are some of the Linux interprocess communication mechanisms. First one is signals. A signal is a notice to a process that an event has been occurred. They are lightweight from the form of the IPC that can be sent between the processes to handle events like process termination or user-defined events. Anonymous pipes. In Linux, anonymous pipes are a type of the IPC mechanisms that allows connected processes to communicate with one another. They offer a one-way data transmission route between the processes. The pipe is created by the parent process using the pipe system call, and it is accessible to the both parent and the child process after forking. The parent processes writes data to the pipe's write end, while the child processes read from the read end. Fifth, first in first out is the Linux IPC mechanisms that allows unrelated processes to communicate with one another. It uses a unique named file as a channel for data exchange. FIFOs are referred to as the named pipes because they have a unique name in the file system which serves as an identifier. FIFOs can be created using the commands like mkfifo or programmatically with the mkfifo system call. sysv message queues. Sysv message queues is a Linux interprocess communication mechanisms that enables the processes to exchange messages via a message queue. The sysv message queue is designed for server applications. POSIX message queues. The abbreviation POSIX stands to Portable Operating System Interface. POSIX message queues are IPC mechanisms that has been provided in Linux since version 2.6.6, May 2004. It allows processors to exchange data in the form of messages to complete their tasks. POSIX message queue is designed for use in real-time applications. SysV shared memory. SysV shared memory enables sharing of memory resources across the multiple processors. It allows for the rapid and efficient exchange of a massive volumes of data between the processors. POSIX shared memory. POSIX shared memory is similar to SysV shared memory but corresponds to the POSIX standard. It provides more adaptable and portable interface for sharing the memory between the processes. SysV semaphores. SysV semaphores are used for the process synchronization and mutual exclusion. They enable processes. POSIX semaphores. POSIX semaphores serve the same purpose as SysV semaphores, but POSIX semaphores calls are significantly simpler than SysV semaphores calls. POSIX semaphores have been available on a libc-based Linux systems since version 2.6. Futex calls logs. Futex logs are lightweight processes synchronization mechanisms. The fundamental goal is to provide a more efficient mechanism for user space code to synchronize multiple threads with a minimal kernel interaction. Memory mapped. File backed and anonymous shared memory using mmap. Memory mapped IPC enables processes to exchange memory regions mapped to the same file or anonymous memory. It provides a high-performance mechanisms for transferring data across the processes. Unix domain sockets. Unix domain sockets are similar to the network sockets but are used for the communication between the processes on the same machine. Unix domain sockets support both the stream-oriented TCP and datagram-oriented UDP protocols. Netlink sockets. Netlink sockets is a Linux kernel socket interface that allows the interprocess communication between the user space and the kernel as well as between the multiple user space processes. Network sockets. Network sockets enable processes to communicate with one another via a network. They provide a common interface for interprocess communication between machines. Notify mechanisms. Notify mechanisms enable processes to monitor file system events such as file changes, creations, and deletions. They provide a technique for handling the file system changes efficiently and reactively. Fuse subsystem. Fuse subsystem allows users to design customized file systems that are implemented in a user space rather than the kernel. It enables the flexible and extensible file system communication between the user process and the kernel. Dbus subsystem. Dbus is a mechanism of interprocess communication between the processors in Linux and other Unix-like systems. It has layered structure. Dbus was particularly designed to fulfill the needs of the current Linux systems. It provides a message bus architecture and supports various programming languages and platforms. Signals Interprocess Communication System. Signals in Linux allows processes to communicate with one another by sending notifications or triggering specific actions. Consider signals to be messages that processes can send one another. For example, when a user hits Ctrl+Z, the keyboard generates an interrupt. The operating system then sends a SIGINT signal to the running process. When a signal is received, the process temporarily suspends its usual execution and executes a distinct block of a code known as signal handler. In Linux, all systems have a default set of signal handlers, reducing the need to handle them individually for each process. Consider the Ctrl+Z signal. Normally, when the user releases the key, the process terminates. However, programs can define their special functions to handle such signals. These functions can be communicated to the kernel using their signal system call from the application layer. When a process receives a signal, the operating system will invoke the corresponding special function defined by the program. Signals are not only used for the communication between the process and the kernel, but they can also be used between the process and the operating system. signals are used by the process to communicate with one another. To do this, a system call function named kill PID ID can be utilized to send a signal from one process to another. Dbus interprocess communication. Dbus is a mechanism of IPC between the process in Linux and other Unix-like systems. It has layer structure. Dbus was particularly designed to fulfill the needs of the current Linux systems. Its major role was to replace the current remote object systems in GNOME and KDE such as Carbo and DCOP. The goal was to build dbus as a universal and a neutral interprocess communication mechanism that could be used by both desktop environments responding to the requirements while bringing new features. Use of dbus. Dbus is a full-featured IPC in Linux and object system that can be used for a variety of tasks. Firstly, it supports the essential IPC, which allows the processes to communicate data like Unix domain sockets with enhanced features. Secondly, dbus enables the transfer of events or signals across the system, facilitating enhanced communication and integration between the various components. Finally, dbus provides a remote object system which allows an application to request services and call methods from a different object. This feature is similar to Corba but with a less complication. Features of dbus. Dbus stands out from the other IPC mechanisms in a few key ways. Firstly, it operates on a discrete messages rather than the byte streams. Each dbus message is made for the data, metadata, and data, resulting in a well-structured binary format. This is in contrast to the other IPC mechanisms in which communication is based on arbitrary streams of bytes with no specified message format. Secondly, dbus uses a bus-based system. While direct process-to-process communication is feasible, dbus includes a message bus daemon that acts as a central hub for routing messages between the processes on a certain bus. This results in the formation of a bus topology in which processes can communicate with one another or more applications at the same time. Why dbus? There are several reasons why dbus interprocess communication mechanism is used. One reason is that the concept of a system-wide message bus is a novel approach where a signal bus is shared by the entire system, enabling events to propagate from the kernel to the highest level applications. Unlike Linux, which has a distinct layers and interfaces lacking integration, the system message of a bus of the dbus enhances the integration while upholding the sound engineering practices. With these bus events, like a disk full, printer queue empty, or low battery power can rise through the system layers, becoming accessible to any interested application. As a result, the system can adapt and react to these environments in real time. The transmission of the events occurs asynchronously and without the need of the continuous polling. Conclusion. A process is a fundamental unit of execution. When a high-level programming language program is compiled and executable file is created, which can be considered as a process. IPC in Linux refers to the mechanisms and the techniques that allows the processes to exchange information, share resources, and communicate with one another. Signals in Linux allows processes to communicate with one another by sending the notifications or triggering the specific actions. Dbus is a full-featured IPC mechanism which allows the processes to communicate data like Unix domain sockets but with enhanced features. IPC in Linux allows the processes that are running on the same system to communicate, coordinate, and exchange the data. The kernel event layer serves as a communication mechanisms between the kernel and the user space, utilizing a high-speed net link socket for asynchronous communication. So that's all for this video. Thank you.